Okay, hello everyone. I'm Lola Fariñas, a postdoc fellow currently working on the Food Physics and Engineering Lab at the Department of Food Technology at the University of Valencia. And I'm gonna talk about devices and sensors that are not in a robot. And I guess that's a novelty here. So my main aim here is just showing the science we are doing and the experiments we are doing with these devices. And if someone thinks that can be robotized or can be useful, just please let me know. If you think won't be useful, please don't say anything to me because you will hurt my feelings. So, well, first of all, this is the sensor. It's the device we used. And basically, this is a low-cost design that we could manufacture in our lab. In our lab, it's not a robotics one, so it's very simple. But the key point, the real sensors here are the ones that are pointed by the yellow arrows, are a kind of cylinders, and we need two. One acts as a transmitter and the other one as a receiver, and must be one in front of the other. And the leaf must be placed in between them. So this design is just because it was, we thought it was easier for the people working in the field to use them. So, well, here, what you see, it's how our data looks. Each red dot is a data point. There are two plots, and what we obtain is what we call, or it's called transmission coefficient, and we obtain basically three different vectors of data. One is independent, which is the frequencies we select to work with, and the other ones, the dependent vectors, are magnitude and phase of the ultrasonic signal. With those, we can obtain direct outputs as, for example, the maximum peak of the signal in magnitude and the frequency at which this maximum is happening, and so on. And those has a meaning physically, mechanically, means something. And also, of course, with data analysis, with several models we built during my thesis work, and with artificial intelligence, we can obtain what I called indirect outputs. It's more data. But here, I'm focused on information. I mean, we can get many different information from the leaf, but today I'm gonna focus on plant water status, since according to the people working closer to farmers in the field, it's very important because they need to decide if they will water or not the field. So, well, this is the current project I got. It's called SID-RAS, and it's just 1 year project. I'm the PI. It's my first project, so it's little money. But basically, we had 54 pots of clemenules. Clemenules is kind of clementinas, I don't know, like tiny oranges, very common there in Valencia. And the experiments is we are gonna make the plants stress. We got a control group with the standard irrigation and two different levels of stress. With 75% of the standard irrigation and 50% of the standard irrigation. And basically what we are gonna do is taking measurements. We have done it earlier, I will show you, with our ultrasonic sensor, and at the same time with the pressure chamber, which is the standard. We will get the potential the water pressure in the leaves at the same time. And probably some, well, like daily cycles monitoring too. But, well, this is our fancy greenhouse in the campus, and these are our 54 pots, very well located, and these are our programming stuff for the irrigation and many other sensors, and we map everything, and we have everything running, all the sensors, and then there are like, I think, 2 heavy rains since September when we started the experiment. So Valencia was flooded, and of course our pots in the greenhouse, because there's only a net, so the water comes too. And we got there afterwards strong winds from one side, and we got problems with the pots. So okay, let's tie all together with a rope, and we started to do some experiments. And the next week we got heavy winds from the other side, from the other direction, and everything with the ropes fall. So, so we got everything ready to start, and I have a few data, but unfortunately I cannot bring you good insights from that experiment because we couldn't make the plants get the stress because everything, all the climate change and all stuff, they are kind of in a standby status. They don't do anything. So we plan to start again in later spring or summer. So I decided to talk to you about what this ultrasonic sensor measures and what that means, and hope you don't get bored. And well, you can ask me, and if I see you are getting bored, then I will go faster and finish soon. It was a long day, I guess. So the thickness resonances is the main principle that what we do. What you can see in the drawing, it's the 2 sensors. The ultrasonic sensors are called transducers. So one of them is a transmitter and the other one is a receiver, but they are built exactly in the same way. And in between, we place the material. In this case, is a leaf. Usually, we don't test leaves. This happened by chance during my thesis. We usually test like aircrafts, and we work with Airbus and stuff to do non-destructive testing, no testing leaves. Basically, the upper plot shows the signal, the ultrasonic signal, when there's nothing in between between the transducers, the transmitter and the receiver, but air. And in the lower plot, what you see is the signal, the same signal once it gets through the material. So basically what happens is that the length of the signal changes, and also the amplitude is the amount of energy in the signal. So if you do the Fourier transform and you get everything in the frequency domain, you get something like this. And the most important part here is the peak you see. That's called resonance. And that's a very well-known phenomenon in physics. That's nothing new. Basically, what happens is that when you ultrasounds are mechanical waves. So basically what we do with the leaf is make the leaf vibrate. But it just vibrates with tiny displacement in nanometers. You cannot see it by naked eye, but it's what we do. So the natural frequency is the frequency at which you get like the higher, the greater displacement of the material. And that depends on the composition of the material, the geometry, and so on. So what we do with this technique is getting that, obtaining that natural frequency of vibration of the leaves. And what we got, we performed this, of course, in several and different species. What we got is that we always obtain something similar of the coefficient transmission I saw you. But if you pay deeper attention, it's not exactly the same. The peaks change, so it's not the same amount of energy, let's say. And the peak, it never appears in the same frequency. So, well, that was the vitis vinifera and the coffee leaf, and this is the tobacco. This is lettuce. This is orange tree, and this is fig tree. So basically, what we got is a kind of fingerprint of the leaf. This was my thesis, so of course I was making a lot of measurements, and these are some of the species we test. So the most important today insights from this resonance we got is the water content effect. So what you are seeing here is an experiment, a short experiment where we detach the leaf from the rest of the plant, and we take one measurement, that's the one that appears the first, this one, and then after a couple of minutes we do the same measurement, and we got the next measurement, and again and so on, and this is what we got, which is a kind of waterfall. And if you pay attention, there are mainly two things changing. There's the frequency, the resonant frequency, which is, again, the frequency at which the maximum appears, is shifting toward lower frequencies. And also, the level of the maximum is getting smaller. So here, there are a few equations, and there's nothing we are inventing here. This is, again, physics. And basically, this resonant frequency is closely related with the elastic modulus, the thickness, and the density of the leaf. That's really, I mean, if you think about it, it makes sense. If we got a leaf and we make the leaf vibrate, it will vibrate with better or greater displacement if the leaf is more stiff, like stiffer, it's more rigid. As long as it loses water, it becomes less rigid, and the vibration changes and gets less, let's say, lower displacements. Okay, so what we did with our colleagues from biology and ecophysiology is test our measurement with the standard. The standard is the water pressure with the pressure chamber. And we did the same experiments with different species, and we compared to the relative water content, which is something that, well, at that point it makes, for me, more sense. It's 1.0, it's full turgor, and towards 0, it's totally dry. And what we got, the darker dots are the inverse of the potential, and the white dots are the ultrasonic measurements. When we got is that we could predict the turgor loss point 99.9% of the time without destruct or detach the leaf and nothing. We don't need to do that. So, well, of course, we do like microscopy, and because we need to check our hypothesis. And after that, we decided that, okay, it seems that we got a new tool, and it seems fun. Why do we need to detach the leaf from the rest of the plant? If we can do monitoring, we can keep continuously making measurements in a leaf attached to the plant. So it's what we do. We put the device in one leaf in different species, different pots in the lab, and we perform in a continuous way every 15 minutes or something like that, measurements during 4 days. And we could see cycles. So if here in the upper plot you can see the same cycles in the last slide. This is vitis again. In the middle you can see the amount of light that was reached in the pot. And in the lower plot, you can see the temperature. It was early summer. So basically, there is a clear inverse correlation between the frequency we are obtaining with our ultrasonic device and the amount of light, which completely makes sense according to the equations I saw you. And also, there was something very interesting too, because we water the pots at our 0, just right after begin the whole experiment, but not until the very end. So what we saw is that the maximum in the frequency, which we get at night, was going down and down and down. So, oops, sorry. Whoa. Here. So we kind of saw that we could probably see some kind of stress in the plant, because the plant couldn't reach the same turgor point as in the first day when it was completely full of water. So, well, we were really happy at this point. I thought, okay, I got the thesis. And, well, we performed many other experiments. I think we don't have time for that, but, well, you can imagine many more monitoring on kinetics of light, kinetics of how fast it recovers for irrigation every leaf. And, well, at the very end, well, not at the very end, but I think like 3 years ago or so, we got a project to develop and use this device. Well, it wasn't a device at the moment because we perform everything at the lab, but to do something more portable. And this project was together with a winery in Fariñas, in Aragon, in Spain. And this is our regional research center also in Aragon, and the CSIC we were CSIC, and we did the same in the field. So we went to an experimental field of the winery, and we performed measurements again with the pressure chamber and with this system, kind of portable that I will show you later, and pre-dawn and midday, and it was a stress. Again, there were water at the very beginning, and then no water during 20 days, and we saw in the frequency measurements the same pattern inversely, but the same pattern that we could see on the pressure potential. You know, like when it gets stressed, both midday and pre-dawn tends to be the same values. And well, finally, this is how the setup looks at the very beginning, because we don't take measurements on leaves. This was new. So we will move in step by step towards the device I showed you. This also changing dynamically. And well, this was the one we used for the measurements in the winery. And the laptop is ugly because it's the one that the ecophysiologists usually use in the field. I don't know, they say it's very robust. And the other thing is the electronics. And well, now a team is working on the next generation, so we are trying to put everything together in the same device, all the electronic sensors and the communication module. And you can control it, of course, wireless. And well, yeah. And finally, our last paper was using not very complicated artificial intelligence algorithms, because we wonder, okay, can we train an algorithm with our frequency measurements in plants in the same location, and that can be tagged with the relative water content? You know, the relative water content is a headache, because you need to take the leaves and you need to use a scale and you need to use an oven. It's something that you need to do in the lab, not directly in the leaf, in the field. So, well, we perform some measurements to do the trainings, and we do random forest and also some neural networks, and we train the algorithms, and it seems like we can predict very well the relative water content of those plants with this technique immediately. So, well, finally, this is the team. The CSIC, where I did the thesis, and Tomás Gómez was my supervisor. He's the keystone of this, because he's a world expert manufacturer designing the transducers, the actual sensors. If you have heard about ultrasounds before, it's not very common to use ultrasounds in air couple. Usually you need water or you need gel, as in medicine. So this is a key point. And then the theta, those are the co-physiologists and the biologists that we were working with during the whole path. And UPV, these are the last ones. The UPV, Juan Manzano, he's an expert on hydraulics. And IVIA, those are the ones experts in a regional research center in Valencia, and they are the experts on watering. KTU, they are Lithuania, they are the experts on the electronics, and well, some collaborations and companies that work with us. And thank you very much for your attention.
Thank you. Unfortunately, the time is running out. Just before the next session.
For me, it's better.
Yeah, I have one question. Sorry, just the price? Because you want to go to the market, you have an idea of the price?
Sorry?
The price.
Oh, okay. So, good question. I cannot. This is this is the regular answer. I don't have a particular. Well, basically, what happens at this point is that we need the electronics. So these people who is working with the electronics, they are researchers too. So if someone wants sensors, it depends on the amount of how many you want. I guess the electronics can go to a company manufactured and do lots of them and gonna be cheaper. The regular system, the one which is with the laptop and stuff, I don't think it's just you talk to my supervisor, and I think there is a price which is already fixed at the moment, because we usually sell those. He usually sells those to Airbus or any other companies. But well, I don't know. I think it's not very clear here, but I think it's way cheaper than the stuff I saw on the downstairs. I can show you. It's for sure.